obviously you can't evaluate this thing without knowing what f of t is, but this is just a definition, so it applies to any f of t. I'll get my pointer out or try. All right, and so what the definition is, as you can see, is that, let's see if this works. Okay, it does now, temporarily, not for long. All right, never mind. We take the function, okay, multiply it times e to the minus st, and then integrate time from 0 to infinity. And that will eliminate time as an independent variable, and you introduce a new independent variable called s. Okay. So the function, instead of being little f of t, depending on time as the independent variable, we call it big f of s, and now it depends on s as the independent variable. Okay. And we'll call that s Laplace variable, Laplace transform variable. Okay. So we're going to go back and forth from something called the time domain, well, you know what that is, to something called the Laplace domain. Okay. The reason we do this is because differential equations are easier to solve in this s domain than in the time domain. Okay. So you're going to have to get comfortable with this idea. By the way, if you guys are, I'm not sure this is a good idea, but if you guys want the lectures, I can in principle email all those to you as well. I mean, I don't have any control over the website, I'm sorry. But so if you decide you're tired of not having the lecture notes, I can email you all the ones from this week, and everyone likes that. This week and last week, and probably, I think I have the ones done for next week as well already. So just send me an email and I'll send them out to everyone. I'll probably send them as PDFs because they're smaller files that way. We usually post them as PowerPoint. All right. So this is the definition, and obviously this is fine. It has to prove useful, and the way it's useful is because of this. Okay, much more convenient to work in the Laplace domain because if you have differential equations, okay, let's say you have a set of ordinary differential equations in the time domain. Once we transform these into the Laplace domain, they'll become linear algebraic equations. That makes them much easier to solve, obviously, because it's easier to solve algebraic equations than differential equations. Okay. So the idea is you're going to follow a procedure that looks like this. Okay. So you formulate, and obviously the model is, if it's based on first principles, always going to be formulated in the time domain. Sometime later this week, I think, I'll show you how to formulate models directly from data in the Laplace domain. But for now, formulate the model based on conservation principles in the time domain. Okay. At this point, assume the model is linear. If the model is not linear, you can't apply the Laplace transform. The Laplace transform will only be applied to linear differential equations. Okay. So assuming it is linear, you convert the model, the set of differential equations to the Laplace domain. They'll become algebraic variables. You can solve it. I'm going to give you an example. A couple examples today. You can solve the problem in the Laplace domain. You can find the answer, and then you can invert the answer back to get the answer in the time domain. Okay. So start in the time domain. Then solve the problem in the Laplace domain, transform the answer back to the time domain to get the answer you want. Okay. May seem, I'm not sure why this thing's oscillating. It is, right?
Yeah.
Okay, just making sure. All right, so this may seem a little bit laborious because it's 3 steps instead of 1, but you'll see, especially when the input has time dependence like this, it's very hard to solve a differential equation in the time domain with time. You don't know how to do it, basically. Okay. So I didn't give you any machinery to do this. So that's going to be the primary advantage of this approach. Okay. So this is just meant to give you some example of how to do this. Now, if you have a book, and you'll need a book at some point, and I believe it's table 3.1 in your book, you'll see that this table has many entries. I think it's almost 2 full pages. And on this side are various functions of time. And over here, the corresponding Laplace transforms of those functions. Okay. So all I'm doing now is deriving a couple of the functions that are in that table just to show you how it's done. But if you needed to take the Laplace transform of this function, let's say, you would just look it up in the table in the future. Okay. You don't need to derive it. But I'm deriving it now because otherwise you have no idea how the entries come about. So I'm just trying to make sure that you have some idea. All right? Okay. So the idea is once I give you the time domain function, you apply the definition, you perform the integration, you get the answer. Okay. So first thing here is what if the function is just a constant called a. Okay. So we just plug it in the definition. You remember the definition is f of t multiplied times the exponential integrate. So I just plugged in a for the function. Okay. Obviously you can pull a out of there because it's a constant. And I'm hoping that everybody knows that the integral of e to the minus st is minus 1 over s times e to the minus st. And I can't teach you how to integrate. Right? The only way I actually know if the answer is correct is I take the answer and I differentiate it and see if I get the integrand back. Right? That's how I integrate. Specify what I think the answer is and then differentiate it, see if I get the integrand back. And if you do that, you'll see you will. Okay. Now you have to evaluate this answer from lower limit of 0 and upper limit of infinity. So you can see the upper limit, e to the minus infinity is 0. That's where you get this. And then you get minus, evaluate the thing at the lower limit, e to the 0 is 1. Okay, so you get minus a over s, two minus signs, a over s. Okay. So constant in the time domain looks like constant over s in the Laplace domain. Right? What if you have an exponential? This guy. Okay. So you plug this into the definition. Okay. And then you perform the integration. So there's the time function, multiply exponential, integrate. You can combine these two using properties of the exponential, right? If you have two exponentials multiplied together, you can add the exponents. That's where I got this here. And if you can integrate the first one, you can integrate this one. It just has a different exponent multiplying time. Okay. You'll get this. If you evaluate the two limits, the upper limit again will be 0. And the lower limit will evaluate to, this thing evaluated 0 is 1, two minus signs, just like that, and you get 1 over s plus b. Okay? So it's kind of weird, right? You take a Laplace transform of an exponential function in the Laplace domain, it's 1 over s plus b, where b is the exponent of the exponential. Okay? All right. So this is a useful and important one, because we do it all the time. Let's say you want to take a Laplace transform of a derivative. Why would you want to do that? Because what you're going to do is you're going to have differential equations. And to apply the Laplace transform, you're going to take the derivative of the left-hand side and the right-hand side. And the left-hand side is always going to be a derivative. Okay? So let's see if I need your help here, if I can figure it out myself. This is the integration by parts. Remember that? You remember integration by parts? So let me see. This is how I remember the formula, I think. U dv equals u v, is this right? Minus integral v du, is that correct? All right, okay. So we have to figure out u and dv, right? That's what we got to do here. So the idea here is you can't integrate this easily, but you can integrate that, right? That's why you do integration by parts. If you can't integrate this, then you've not accomplished much, okay? All right, so let's see what's defined to be what. So I used to have a little sticky note that told me which one was what, but that's all right. Okay, so that's the integral part here. And so we'll get f and e to the minus st. So the original one. Okay, so let's see if I'm correct here. My guess, I'll probably be wrong here. If you see me going down the wrong trail, you should correct me, okay? My guess is that v equals f. And then, right, dv will be the derivative of f. That looks maybe promising. Right, this thing here, if we look at what u dv is up there, this dt cancels, right? It's df e to the minus st. So I'm thinking that v is equal to f and dv is df. And that means u has to be equal to e to the minus st. Okay, and du is minus s. Yeah, thank you. This differential. All right, let's see if this all works out. At least u dv is right? Because u dv has to be df, which is that, and then e to the minus st, which is that. Okay. That's fine, sorry. Okay, and so now we have to compute what is u times v. So u times v should be f times e to the minus st. Okay, that's that part right there, it's u times v. Evaluate the limit. And then we have minus v du. So v is df. Okay. No, sorry. V is f, and then this is du. Okay. So you can pull out an s. Do I do that? No, it chose not to. Okay. So this is the other term. It's plus because there's a minus sign there and a minus sign there. Okay? All right. So let's see if we've accomplished anything by doing this. The idea is you have to be able to integrate this thing. Okay. The fortuitous thing here is if you pull out the s here, which you can because this is integrate expected t, this is the definition of the Laplace transform of the function f. Right? So you pull the s out. So that's where I get this thing. That s, pull it out, and what's left is the definition of what I mean the Laplace transform of the function, just by definition. Okay? And then I have to evaluate the lower limit, or sorry, this other part here. So again, the upper limit will yield 0, and the lower limit will just evaluate to f of 0. In other words, the value of the function at time equals 0. Okay, so this is what makes the Laplace transform so useful. Okay, because what was a derivative now is not a derivative. So when we apply this to differential equations, we'll get algebraic equations. Okay. All right. And you'll see how this all works. If you had a higher order derivative, you don't really need to worry about this one, to be honest with you, because we never have second order derivatives in time. Right? If you write out an accumulation term in a chemical engineering problem, you don't get second derivatives. But you do in mechanical problems and things like that. So you can apply this to a derivative of any order, but this is the key one right here. Okay? So what you want to start thinking about now is that if you see an s multiplying the function, that means this function is integrated. Okay, that's what s means, integration. Okay? Correspondingly, I don't derive this one, but if you want to take the Laplace transform the integral of the function, so this is the Laplace transform the derivative of the function. What's the Laplace transform the integral of the function? The second step's not very useful. I just apply the definition. I want to show you how you do it. Okay? What do? Well, you take this thing, you multiply it times e to the minus st and integrate it. If you perform all this, I don't know if it's derived in the book or not, you get minus 1 over s times the Laplace transform of f. Okay? So 1 over s means integration, s means differentiation. Yeah?
What if we don't know the form of the function f of t? Can we use capital F for that?
Yeah, in many cases you're trying to actually solve for f of s, because that'll be the solution you're interested in. And then you can invert it back to time. I'll show you in a moment how to do it. Okay. So this applies for any function f and any function f here. I didn't tell you what the function was. So whatever the function is here, it's the Laplace transform of the derivative is this. So this is the Laplace transform of the function f. To write that, you don't even know what the function f is yet. Okay? And typically what we'll be doing is wanting to solve this equation that we end up getting for f of s, and then we invert it back to the time domain, which I'll show you to get the answer, f of t. Okay? Oh, you'll see all that. Okay, so at this point, you want to start thinking, if I see an s floating around, it means differentiation. If I see a 1 over s floating around, it means integration. You'll see how this works. Okay. All right. So at this point, I don't want to derive any more of these things. Okay. So if you look at your table, you'll have some really gnarly looking entries. Hold on a second. In this table, and these will be things that look really weird right now, but they'll be common things that you'll see in the problems that we address throughout the course. Okay. So at this point, if I give you a time domain function and tell you to take a Laplace transform, the first thing you do is go to table, I think it's 3.1, and try to find it. And if you find it, the answer's right there. Okay, you're done. You don't need to perform this integration. Okay, question?
That was my question. What table number was it? 3.1?
I think it's 3.1. Yeah. It'll be, you won't mistake it for anything else, trust me. All right. Okay. So here's some properties of the Laplace transform that we'll use, okay? So the Laplace transform is a linear operator. And so for any linear operator, you have this concept of superposition. I don't know if you've heard that term before or not. I would think so, but maybe not. So let's say for whatever reason, I need to take the Laplace transform of that thing. A constant a times a function f plus a constant b times a function d. Okay? Because this is a linear operator, the answer is, first of all, you can split these two things apart and take the Laplace transform of that thing plus the Laplace transform of that thing. Okay? And when I take the Laplace transform of that thing, I can pull the a out. Okay? So that means the answer is just the constant a. F of s is the Laplace transform of f, little f. And then you have b plus g of s, where that's the Laplace transform of the function little g. Okay? This will, it's like, this will come up at some point. You just have to trust me now that it's useful. All right? Okay, now this is not true if the operator is not linear, right? So if the operator was square things, this obviously wouldn't be true, but the Laplace transform is a linear operator. Okay. So here's something I'm going to give you without proof, but is quite useful. Okay. So let's say you want to know this. Okay. You want to know what the limit is of some function y of t as t goes to infinity. Okay. But you don't have y of t. Okay. You have its Laplace transform, capital Y of s. Okay. What this allows you to do is to find this thing directly from the Laplace transform y of s instead of the time domain function y of t. This can prove quite useful because, as we'll soon learn, the final step in solving differential equations is invert the answer back to the time domain, and that's usually the bottleneck, as you'll soon see. Okay? So if the only thing you want to know is what is the final value of the function y, as t gets really large, you can find that directly from the Laplace transform. The way you do it is take the Laplace transform function, multiply it times s, and take the limit as s goes to 0. This may seem like a bizarre thing, because right, s is here, you think it's always 0, but usually there'll be an s in the denominator of this y, you'll see. They'll cancel, and it won't always be 0. Okay? Now there's a caveat here. You have to know this limit exists in the first place. Okay? So, if this limit does not exist, in other words, this thing becomes unbounded as t goes to infinity, this is not true. But soon you'll be able to look at y of s and know whether this is true or not directly from the y of s. You'll see. Okay? So that's useful. This one is less useful, but true. Okay? If for some reason you wanted to know what's the initial value for y, and you have the Laplace transform instead of the time domain function, you can apply this. Take s, multiply y of s, take the limit as s goes to infinity, and that'll tell you what the initial value of y was. Okay. The reason that's not very useful is because usually I give you the initial value of y, because to solve a differential equation, you typically need that. Right? Like if we had a differential equation that was dy dt equals something, I would usually give you y of 0. You wouldn't really need to do this, but, for completeness. Okay, so here comes the, I was going to call it the first mind twister or something. This tends to be a concept that students have trouble with and takes them a little bit of repeated exposure to get it down. Okay. Let's say you're interested in this kind of function. Okay. You see that this is just some arbitrary function drawn here. Okay. This function is the same as this function, except it's just been translated along the axis. Right. It's been translated t naught time units along the axis. This t naught is called a time delay. Okay. This happens a lot in chemical engineering problems because you frequently have transport delays and time delays. Like let's say you had a chemical reactor. Right, so you have this reactor here, and you put ingredients into the reactor. And of course, the way they do it in a real plant is they connect the pipes wherever it's convenient. And so they may decide they'll add the ingredients at this point right here. Okay? Why? Because the piping is easy to do that way. It's easier than to run that pipe all the way over to the reactor. Well, if you change the relative amount of, let's say, A and B, it'll take some amount of time for that to propagate to the actual reactor. Right? And that amount of time we usually call it theta or TD over there. Or T naught. That amount of time is called T naught. Okay? It's the amount of time it takes for an element of fluid, let's say, to go from this point to this point. In other words, if I change the mixing here, the amount of A and B, the reactor's not going to see that until T naught time units later. This has a big influence on control. Okay? If that T naught is big, it becomes very difficult to control the reactor. Because you do something, but it's not reflected in the reactor until some time later. Okay? Ideally, you wouldn't have these time delays because someone would just take this thing and say, why don't I just put it right in the reactor there? And then this would be eliminated, but that's not how plants are built. Okay? Because piping costs money, and so they'll mix wherever they want to, not where you want them to. All right. So and then another possible source of the time delay is a measurement delay. Like you want to measure something, you've got to take a sample from the reactor and bring it to some device that actually does the measurement. That'll be a delay also associated with piping and tubing. Okay? So you'll see these kind of delays come up a lot. Okay? And so what we're interested in here is what is the Laplace transform of this function? We know what the Laplace transform of that function is called capital F of S. What's the Laplace transform of that function is the question. Okay. All right, now first of all, you'll have to wrap your mind around this. I'm representing the function like this. Okay, what does this mean? Okay, let's forget the S thing, I'll explain that in a minute. This should make sense. The delayed function is a delayed version of the function f, right? So if you, for example, what is the value at t equal t naught? Well, you evaluate this at t equal t naught, and so, is that right? Right, f of 0. So, sorry, if you evaluate this function at t naught, this evaluates to 0. So the value of f of d at t naught is the value of f at time equals 0. So that function just translates this function down the axis, just like the picture. Okay. The reason you have to append this thing, first of all, let me explain what that thing is. Erasers are... that S function is something called the unit step function. Okay. So it looks like this. And here's S of t, and here's t. Okay? And here's 0. Okay? This is a function that is 0 until you get to time equals 0, and then it jumps up to a value of 1. Okay? So what is the function? That's not why I have this function S of t minus t naught. Well, that's a function that's going to be 0 until t naught, and then it's going to jump up and assume a value of 1. I'm just telling you that's the definition of that function, unit step function. Okay? Why am I multiplying this times the function that makes sense? Well, because this thing, so if you ask me, what is the value of this function here? Okay, well, to find the value of this function here, I'd have to have values of this function less than 0, and that's not allowed. The Laplace transform doesn't allow you to do that. Okay? So in other words, currently the values here is undefined because I don't know what the values are there. So what this thing is, it constrains this function to be 0 until t naught. That's what this does. Okay? That's what this part does here. And after that, it assumes a value of 1. So it doesn't matter what this thing is here. You don't need to know it. This ensures that it's 0 until t naught, and then it assumes a value of 1 and is irrelevant. Okay? All right. So with that in mind, that way I don't need to know values of the function at negative time. I'm just telling you the Laplace transform of this function, which is this picture, is this. Okay? F of d, capital F of d is Laplace transform of little f of d. So it says take the Laplace transform of f of s, that means the transform of the undelayed function, and multiply that times e to the minus s t naught, where t naught is the delay. Okay? So in other words, the Laplace transform of a delayed function is just the function without delay times this exponential term that accounts for the delay. Okay? So if you see a term like that floating around, that means your problem has a time delay in it. Okay? And these will have various implications. Not surprisingly, this is not a major step here. You can go the opposite way. I guess we haven't really talked about the inverse Laplace transform. But, so if I aspire to, let's say, find f of s, then I apply the Laplace transform to little f of, t, right? And that's what we've been doing. I might want to go the other direction. I want to know little f of t, and to